Hey class, sorry that I misspoke last time and when discussing the due date for the exam. So I had originally scheduled it for Tuesday, but I like Thursday due dates. What can I do? You'll be fine as long as you get it in by tomorrow. Some of you have discussed individually extending it a little bit further. And that's fine if that's the case. If you need an extension, reach out to me and let me know. But whether you need the extension or not, get to work on it. Don't wait. Get the work in, get it done, and move on. Not just for this class, but for your other classes as well. You don't want to get bogged down with just a single course's material. Okay, so let's continue the grind and see how much further we can get. I feel pretty good about our chances of finishing the lecture notes in general before spring break, and then we can start the what I consider to be the more interesting discussions in computer science and as they apply to discrete as well. Okay, so we left off on partial orderings. And so I mentioned lattices and how they're an example of partial orderings, and how we were using subgroups, which are very similar to subsets in terms of notation. But the concept is a little bit similar as well. So a group it's a set, but it defines an action, sort of like multiplication or addition. And whenever you perform that action, then the output is still some member of that group. It's a set with an action. So like the natural numbers and the integers, you can add things, and then they also have additive inverses. Right? So you can add things, and you can we call it subtracting. You can add the negation of that element, the additive inverse of that element. And when you do that, you get the identity for the set. And so the integers are a group with respect to the addition operation. And then not exactly with multiplication, because you don't have that every element has an inverse that's still an integer, right? So the number 2 doesn't have a multiplicative inverse, so something that will give you the multiplicative identity 1, which is still an integer. So 1/2, which is the unique multiplicative inverse for 2, doesn't yield or isn't found within that original set, right? So the integers are not a group with respect to multiplication. Right? So if you understand the concept of sets and of just this either finite description of some collection of elements, or infinite as in the case of integers, then groups aren't terribly far away in terms of understanding. Okay, but let's jump back into to partial ordering. Right? So again, most of what we're doing with the lecture notes, so I've mentioned this before, but it kind of toggles back and forth between definitions and theories, and then examples of either the definition or the theory to understand. But a lot of what you're doing is just learning the lingo, learning how to speak in some common tongue, where you can refer to some common concepts with other people in the field. So it's not the most fun part. I think the problem solving tends to be the most fun, but it's the barrier to entry a lot of the time. It's just grinding through the definitions. So okay, so keeping in mind that this is a necessary step, the definition for partial ordering with a relation R on some set S, it's satisfied if if it's reflexive, anti-symmetric, and transitive. And remember, anti-symmetric said that if it's symmetric, then you have equality. Right? And transitive is if A relates to B and B relates to C, then A relates to C. So a set S together with a partial ordering R is called a partially ordered set, or poset, supposedly. I never called it that. And is denoted S R, right, where the members of S are called the elements of the partially ordered set. Okay. So, for example, the greater than or equal to relation is a partial ordering on the set of integers. So it's not totally ordered, but it's partially ordered. So the reflexive requirement A equals A is satisfied, right? A is less than or equal to A, always, to itself. Right? The anti-symmetric requirement, if A is greater than B and B is greater than, if A is greater than or equal to B and B is greater than or equal to A, then we have that A must equal B, and that's satisfied by this operation. And then the transitive requirement, A greater than or equal to B and B greater than or equal to C, implies that A is greater than or equal to C. So, according to this definition, right, with these three requirements, reflexive, anti-symmetric, and transitive, then from the definition, we can state that this operation satisfies all the requirements, and so combining that with the set, and so it's an operation or a relation combined with the set, and so with the set of integers forms a partially ordered set. Okay. So the set S is the set of elements. So here it's the integers, and then the relation or the operation. Right? So greater than or equal to. Okay. So notation, just we mentioned in passing that we'll represent this. So here we used greater than or equal to. It's equivalently you could say less than or equal to. Okay? And so the notation A relates to B is used to denote this relationship between A and B in our relation. Right? In some arbitrary partially ordered set, the set of elements in the relation, right? So this is some generic symbol, right? This can mean less than or equal to. It can mean a subset. It can mean anything, and so it's just the generic symbol that's used to refer to the relation of a partially ordered set. And so this is used as a placeholder as opposed to using a letter such as R to represent the relation operator. Okay. Next definition. So the elements A and B of some partially ordered set, S with the generic placeholder, right, are called comparable if either A relates to B or B relates to A, right? So if either we can compare A to B or B to A, right? Or rather, if their relationship is defined with respect to the relation or the operation or whatever you want to call this on the set of elements. And if they can't be related, right, then they are not comparable. Okay. So, so for example, one of the problems that you run into for sports fans, right, is like, what is the greatest basketball team of all time, or the greatest football team of all time? And so you run into this issue where you can relate them within a given year, right? Whoever won the championship has an argument or has a claim to be the best team for a given year. And then you can also say that, well, some teams, some years, you have this really special team that's better than others. But then how do you compare those local maxima, right? The best teams in a given decade or whatever to other teams. And you can't make that comparison. So you have that relationship between teams and that championship team in a given year, but you don't have a relationship defined between teams across years or across decades. Right? So they're not really comparable. They're incomparable. Right? So so you could define some metric, right, like most points scored or whatever, but the rules change, the talent pool changes, and so forth. So So that's an example where you can make comparisons between some elements, but not between all elements. Okay. All right. So next definition: if S and our relation is a partially ordered set, and every two elements of S are comparable, then S is called totally ordered, or linearly ordered, right? And the relation is called a total order or a linear order. A totally ordered set is also called a chain. Okay, yeah, so we're going to give an example of a totally ordered set down here. Okay, so the pair S and the relation is a well-ordered set if there's a partially ordered set such that the relation is a total ordering and every non-empty subset of S has a least element. Okay. So when would this not be the case? So I want you to consider the case of the natural numbers versus the integers. Right. So the natural numbers are the positive integers, and the integers as a whole are both all of the positive and negative numbers. Well, that set is totally ordered. You can compare every pair of elements in there, and you'll get a clearly structured ordering, right? But only the natural numbers are well ordered, right? Because of this requirement, and this is by definition, right? So they're both totally ordered because it's just a smaller set of a totally ordered set as far as the natural numbers are concerned. But every non-empty subset of S has a least element. Well, if you consider just the negative integers, right, then it's non-empty, right, and it's a subset of all of the integers, but there's no least element, right, so you can't begin the set. And so the idea behind a well-ordered set, if you think about looping over an array or a collection or something, then this definition just says that the collection is well ordered, or your partially ordered set is well ordered, if you can start the loop somewhere, right? You have some first element that you could enter into. And so if you're using the less than operator, then the negative integers have no first element. And if you're using the greater than operator, then the positive integers have no first element. Right? So you can't list them out in that way. But if you reverse that, if you start with the maximum of the negative integers, then you have that entry point. Right? So it's well ordered in that direction. And if you start with the minimum of the positive integers, then you again have that entry point, and so it's well ordered. So that's the distinction between a total ordering and a well ordered set. Okay, so now we have a theorem on that, the principle of well ordered induction. So suppose that S is a well ordered set, then the property or proposition P of X is true for all elements of our set S, if for any element that we choose Y from our set, we have, or for every element, for all elements in S, we have that P of X implies P of Y for all X related to Y, or all X less than Y, or all X which precede Y. So if you remember, by induction, we begin with some entry point, we begin with some basic step, and then we sort of march our way forward. And so all of the examples we did, we started with either 0 or 1, and then we showed that you can make it from 1 to 2, and then you could make it, if you could make it to some integer k, then you can make it to k plus 1. And so that actually, those arguments, if we could find an appropriate example, would have held going in the other direction. So that you could have, you could begin with -1, and then show that it holds true for -2 up to -k, and then from -k to -k plus 1. or negative k minus 1, however you want to look at that. If you put it in parentheses, it's negative parentheses k plus 1 close parentheses, right? So you can go in either direction, right? In the well-ordering set, this principle tells us that, essentially. So whatever direction you're going, if it's well-ordered, then you can begin with some entry point, right? And then for any element which succeeds that entry point, you have that this property holds true. So you can use induction for more than just those cases we initially looked at. And that's according to this theorem. Okay, so now going on, the example of something that's totally ordered. The lexicographic ordering relation operator, so we'll say less than or equal to, right? And so lexicographic is just dictionary ordering or alphabetic. On some set A1 cross A2, or the product of A1 A2, is defined by specifying that one pair is less than a second pair if the first entry of the first pair is less than the first entry of the second pair, or if the entries are equal. But the second entry of this pair is less than the second entry of the second pair. Alright, so that's kind of a mouthful. We probably read that several times and not really understand what it's trying to say. But again, this lexicographic ordering is dictionary sorting. So if we're doing it on a single word, then we compare the first character of each word. So everything that begins with an A precedes everything that begins with a B. If two words begin with an A, then you move on to the second letter and make your comparison. If you have another tie, then you move on to the third one, and so on and so forth. So for here, we're just using two examples, right? We're using essentially words with only two letters. And we say that this holds true if either this first comparison yields precedence, right? So if this becomes before this, or in the case of a tie, if the second one indicates precedence of this over this, right? And so, all of this, for all of the new nomenclature and symbols, it's just saying kind of what you already know in terms of how to sort things in dictionary form or in alphabetical order. But it does it generically because, again, we're dealing with relations, and relations, I want you to think relational database, right? And so, imagine that you're sorting a student's grades, right? And so the first comparison, or you're sorting the entire class's grades, right? And so the first comparison is by student ID, right? But if you have two records, right, so the first one, both of these refer to the same student, well, then the next thing you're going to do is, when did that student take the class, right? So order them by student, but within a given student, order them by date of the class completion. And then if there's a tie there, right, so they took them in the same semester, well, then order them by course number or something like that. So you would give some third criterion, right? And so you can think of this, so that alphabetic sorting, lexicographic sorting, is just our way of saying that you can continue to make these comparisons, field by field, sort of breaking ties along the way, and then the first time that you have a tie broken, then you have defined which record should precede the other, right? And so you'll use this all the time whenever dealing with sorting relational database return sets, or in code, whenever you sort, you'll specify the comparison function. You'll say test this value first, and if that's a tie, then you test this value, and so on and so forth. So you use it all the time, and you'll never think about it. Okay. All right, so the next definition is on upper and lower bounds. So if U is some element of S such that every other element, or all elements of S precede U, right? yeah, this is garbage, right? So no, it's saying it right, but this should also be the set A, right? I don't know why I left it as the set S, but these are the same set, right? So if for every element, right, of well, okay, maybe not. So A can be a subset, right? This can be some finite collection of integers, right? And this can be the overall collection of integers. And so we can pick some element which is outside of this, but which, right? So if we have the numbers 1 through 10, then we can pick the number 100, right? And it acts as an upper bound for everything that's in our set 1 through 10, right? So there's a lot of subtle things going on here where we have that this relation comparison is pulled from some parent set, and then we use that comparison. So like in the case of the numbers, where we pull an upper bound and the relation operator and compare it to all of the elements of some smaller set, right? A and A. Anyway, so when we do that, right, when we pick something that's bigger than everything else, then it's called an upper bound. Right? And then on the other hand, if we pick some element L, drawing from that larger set, which is less than, or which precedes every element in our smaller set, then L is called a lower bound of A. Right? So it's exactly what you would expect, but we can use it more generically. Right? So whenever we have those that comparison defined, then we can define these upper and lower bounds. And so remember, not everything is guaranteed to have. So this only defines some partially ordered set, and so it may be that some of these elements are not comparable, right? So that you can't actually draw some upper bound or lower bound. So it's not a given that you're going to be able to find that. But if it exists and it satisfies this criteria, then it's an upper bound or a lower bound. So then now the least upper bound, right, if it exists. So some element x is called the least upper bound of that subset A if x is an upper bound that is less than every other upper bound, right? So in that case, in some cases, right, it's the maximal element from this subset. And so I want you to consider the real numbers, right? So if you have the closed interval 0 to 1, right? That's a subset of the real numbers. It's every number between 0 and 1, including the boundary points 0 and 1, right? That's what it means to be a closed set. Then that least upper bound is going to be the number 1, and that occurs within our subset, right? But if you consider the open interval 0 to 1, so it's all of the values between 0 and 1, not including the limit points, not including 0 or 1, right? Then the least upper bound is outside of the set that we're considering, right? But in both cases, for the closed and the open interval, that least upper bound is the value 1, and the greatest lower bound is the value 0 for that example. Right? Okay, so if we have it and it's the smallest of all upper bounds, then it's called the least upper bound. And because there's only one such element, if it exists, it makes sense to call it the least upper bound. So it is unique whenever it exists. Yada yada yada. Okay, and likewise, if you come from below, then you can define some value y, which is the greatest lower bound of A, that subset A, if it's less than, or if it's greater than every other lower bound, right? Right. In such a case, it's unique, and we would call it the greatest lower bound. Okay, so we mentioned the latest last time. A partially ordered set in which every pair of elements has both a least upper bound and a greatest lower bound is called the latest. So you can compare them right to the upper bound and the lower bound. So there was a unique top of the lattice and a unique floor of the lattice. Right? So there was upper bounds and lower bounds, least upper bounds and greatest lower bounds in that example. And so so now we have that it's a data type, right? It's a concept that is we can call a data structure. It obeys certain properties, and its elements are going to be sets. Right? Okay, so you probably won't see that a whole lot unless you study algebra pretty far. Okay, so then the next definition is a total ordering with our relation operator is said to be compatible with the partial ordering if with the partial ordering R if A relates to B whenever or if A precedes B whenever A relates to B, right? Okay, so yeah, that's just saying that sometimes the operation carries over, and in such a case, whenever it does, then it's compatible. Okay, so now, lemma. Every finite, non-empty, partially ordered set, S, combined with its relation operator, has at least one minimal element. Okay. So there's at least one minimal element. But it can be that every element in the set, if none of them compare to each other, which is a bit of a tragic choosing of your elements, right? But if none of them compare, then the entire collection is the least, right? They are all minimal elements and all maximal elements. Anyway, so note that this minimal element is not necessarily the same as the global minimal element. Okay, so partial orderings are nice to keep in mind, and the lexicographic ordering is probably the most important thing, that concept that you'll encounter from that last section. But you're not likely to use it extensively unless it comes up in some form of specialization. Okay, but graphs are definitely something you're going to want to keep in mind. Okay, so definition: a graph, we'll call it G, is actually a pair consisting of a set of vertices and a set of edges. So the vertices are some non-empty set, and the edges, they can be empty. Right? They can all be these isolated points, and that's a graph. But so there is no requirement that E be non-empty, but the vertices must be non-empty, otherwise it's not a graph. Okay, so each edge has either one or two vertices associated with it, called its endpoints. An edge is said to connect its endpoints. If you're looking for some example to keep in mind while we go through graphs, you can think of computer networks. And so the edges are either, if you're running Cat5, then it's the physical cable that connects one node to another. Otherwise, it's the wireless connection. So whenever one device connects to another, then the edge is wireless. It's conceptual, but that connection is there. Okay. And then the other example that's nice to keep in mind is like the interstate highway system and how it connects cities. So then the cities would be the vertices, and the roads that connect them would be the edges. Okay, so now next definition: a graph in which each edge connects two different vertices and where no two edges connect the same pair of vertices is called a simple graph. Right. Okay, so if you consider the interstate highway example, then that would be a simple graph. There are no interstates where well, I'm saying this, right? So there are these loops, right? These interstates that have these loops in the that kind of go around a city. So in some sense, they connect the city to itself. So throw those out, right? Get rid of all of the loops, and then you have a simple graph in terms of the interstate system. And so there's no pair of interstates. Well, I say that, and I think 30 and 20 both connect Dallas to Fort Worth, right? So in that case, it's still not a simple graph, even if you get rid of the loops, because there are two distinct edges which connect the same two vertices, Dallas and Fort Worth. So while the interstates the interstate system is a great example of a graph, it is not itself a simple graph, and for those reasons. And so those are the exceptions that you're trying to get rid of whenever you want to describe a simple graph. So there's no requirement that everything be connected, but when there's a connection, it's not self-referential, it's not looping back on itself, right? And it's not redundant. It's whenever two things are connected, they are uniquely connected. Okay. By direct connection, not necessarily by path, right? So you can go from A to B via two different routes, possibly, right? But you can't go directly from vertex A to vertex B by more than that single edge that connects them. Okay, so next, graphs that have multiple edges connecting the same vertices are called multigraphs. So this would be the interstate, right? And then an edge that connects a vertex to itself is called a loop, and these are the loops in our interstate system. Where I think there's a loop that goes around Houston. I can't remember. I don't think there's an interstate loop though, but let's see. 635 is a loop. I'm not sure if it actually properly goes from Dallas to Dallas though. I want to say it goes from like Irving to Dallas or something like that. So that might not be an example, but there's bound to be some loop, maybe in Baton Rouge, maybe in New Orleans or something, that connects a city to itself. Anyway, but that is a loop. In terms of the networks, there is always the loop back interface. You can access websites hosted on your own computer via the IP address 127.0.0.1. So networks always have loops. Every device has a loop back. Okay. Next, directed graph, supposedly referred to as a digraph. Again, I don't call partially ordered sets post sets. I don't call directed graphs digraphs, but maybe some people do. So this is a pair, and it's just like the graphs, right? So it's a set of vertices and a set of edges. But in this case, the edges are directed edges, right, or arcs, and so they have a source and a destination. So it's an ordered pair, right, and the directed edge associated with the ordered pair is said to start at U, so source, and end at V, destination. Okay, next definition. So two vertices, U and V, in an undirected graph G are called adjacent or neighbors, and you've heard me mention adjacency graphs or adjacency matrices. Adjacency matrices, and it comes from this, right, where you're just indicating that there's a connection. Right? So the vertices in an undirected graph are called adjacent or neighbors if in our graph, if U and V are endpoints of an edge in G, right? And so it's undirected, so it doesn't matter. It's just a pair. It's not an ordered pair. um, so long as there is an edge that connects them directly, then they're adjacent. Such an edge, E, is said to be incident with the vertices U and V, and E is said to connect U and V. So we'll have adjacency matrices, and then we'll have incidence matrices. And so I like incident because whenever you consider like physical cable running and connecting to nodes, across cities or whatever, then the incident, like if there's an accident or whatever, the incident occurs on the cable. Anyway, but that's different context for the meaning for the word. Anyway, so the incidence matrices will be with respect to the edges, and the adjacency matrices will be with respect to the vertices. But you'll see that distinction. So the rows and columns in an adjacency matrix will both be vertices, and the rows in an incidence matrix will be vertices, and the columns will be edges. Okay, so next definition. The set of all neighbors of a vertex V of some graph, which is the pair of vertices and edges, denoted by in a V, is called the neighborhood of V. If A is a subset of V, we denote it by neighborhood of A, the set of all vertices G within G that are adjacent to at least one vertex in A. So this is essentially your choice, right? The feds are banging down your door and you gotta run, right? Sorry, I've been watching a lot of Breaking Bad lately, again. So, you gotta run, right? You gotta go somewhere. Then you check your neighborhood. What are the neighboring cities? Where can you bolt to? Or what are the cities closest to you where you know someone that you can spend the night with, or something, right? Somewhere that you can camp out for a night, right? Or less illegally than if you're talking about networks, right? Then the neighborhood of some computer or of a router. You can consider this from the perspective of the router. Are all of the devices that are directly connected to that router, right? So in the case of a router, then in one direction it's either connecting to the modem or it's connecting directly to your internet service provider, and then in the other direction on the intranet, it's connecting to all of the devices that are connecting to the router. Okay. Okay, and so this was the neighborhood of a single vertex, right? But we can choose some subset of the graph, and we can define a neighborhood on that subset, and it's just the union of all of the individual neighborhoods. Okay, so now the degree of a vertex in an undirected graph is the number of edges incident with it, except that a loop contributes twice to the degree of that vertex, right? So we're saying edges, but it's not distinct edges if you count loops. So a loop counts twice, essentially, and we don't correct for it. It's still it's counted twice whenever you consider the degree. So it's all of the edges connecting to external vertices or different vertices, and then each edge that's a loop back counts twice because it goes out and then it comes back in. And so out and in both contribute to the degree. Then the degree of vertex V is denoted by the degree of V. And again, that's defined on an undirected graph. Okay, so A vertex of degree 0 is called isolated, right? So if it's not connected to anything, then we just say it's an isolated point or an isolated vertex or an isolated node. All right, so now we have a theorem, handshake theorem. So we're given some graph consisting of the vertices v and edges e, which is undirected and has m number of edges. Then twice m is equal to the sum of all of the degrees of the vertices individually. Right? That makes sense, right? So, and this lines up with our definition up here, right? For a loop back counts twice. And so, essentially, if you were to walk the network, so to speak, then you would go from you would start at some location, you would travel to another one. And so you left that first location and then you arrived at the second one. And so that same edge counted for 1 degree at your source and then 1 degree at your destination. So we counted it twice. And then every connection essentially has that property where it's counted at the source and at the destination. So each edge contributes 2 degrees, source and destination, even if it's an undirected graph. I'm just using this term generically. And so, but each edge has 2 endpoints essentially. And so that's all this is saying, is that if there are m edges, then the sum of all of the degrees will add up to twice m. So note that this theorem applies even if multiple edges and loops are present. Okay, so even if you have the same city connected by more than 1 edge, or the same pair of cities connected by more than 1 edge, that theorem holds. Okay. An undirected graph has an even number of vertices of odd degree. Okay, yeah, and so that follows from this, right? So the sum is always going to be even, right? So if you have some vertices which are of odd degree, or then you're going to have an even number of them. Okay, so then when you have a pair, UV, which represents an edge, right? So if you have some edge of the graph with directed edges, then U is said to be adjacent to V because we can travel from U to V. And V is said to be adjacent from U. Although I will never use this, right? I'll always say that U is adjacent to V because you can get from U to V, but you don't know whether or not you can get from V to U. Right? The vertex U is called the initial vertex, right? And the vertex V is called the terminal vertex, or the end vertex of that edge. The initial vertex and terminal vertex of a loop are the same. That kind of goes without saying. Okay, so then a complete graph with n vertices, denoted K sub n, is a simple graph that contains exactly 1 edge between each pair of distinct vertices. Okay, so the complete graph, trying to think of a decent example here. Okay, so let's say you wanted to form a telephone network with your friends using empty cans of corn or something like that, right? Empty tin cans connected by a string. Then there's no routing such devices. You have to maintain some amount of tension on the string, and it really only goes from one tin can to the next tin can, right? So then your graph, like the number of people, like if everyone wanted to be able to talk to everyone else in this can of corn network, right, then you would need a complete graph, essentially, where every pair of individuals has a tin can that connects directly to each other, like one can for each other person in the network, right? So then such a convoluted thing is your complete graph. But let me draw this on the whiteboard so that you can see what we're looking at. Okay, so A connects to every other node. Right. B is already connected to A. So we need to run a can of corn from B to C and B to D. C is already connected to A and B, so the only connection that remains is D. Okay. And then now D is connected to A, B, and C. So each vertex, or each node in this graph, is connected to every other node directly, by direct line. So that's a complete graph. Okay, so a cycle, when it exists, is a path which visits each node of a graph exactly once, terminating with the node of origin. Right? So this is like a paper route, right? So in the ideal paper route, you deliver the newspaper to every one of the subscribers, and you don't repeat yourself. You're not going up and down the same road multiple times. You make it in exactly one direction, and then you end up back at your house where you started. So that's a cycle. Okay, so a simple graph G is called bipartite if its vertex set V can be partitioned into two disjoint sets V1 and V2, such that every edge in the graph connects a vertex V1 and a vertex in V2. So there's no edge connecting any pair of vertices from V1 to V1. Likewise, no edge connecting any pair of vertices which are both in V2. When this condition holds, then the pair V1 and V2 are a bipartition of the vertex set V and G. Okay, so that one, probably not terribly intuitive what's going on. Right? Okay, so let's say that you have, this is like a dance partner condition, right? So, like, sure, Dancing with the Stars or something like that. So you have all of the professional dancers over here. Right. And so there's no requirement in this case that that it be fully connected or whatever, that there's any path condition. So we just require that we can separate them out in this situation. So we can separate them out into two distinct sets, where no pair of professional dancers is paired with another professional dancer competing against, some pairing of amateurs, right? So it was one from this set, right? One from the pros, and then one from the amateurs. So that's a bipartition of a graph. Okay. So now a subgraph of G, where again, we've defined the graph as a pair of vertices and edges, is a graph, something that is itself a graph, consisting of some subset of the initial set of vertices, where V1 may in fact equal the initial set V. So sometimes we restrict the vertices to some subset of vertices. Sometimes we restrict the edges to some subset of edges from that initial graph. Right? And so for a proper subgraph, at least one edge and or one node must be removed. So proper subsets mean that there's that one set is truly fully contained in a larger set, not greater than or equal to, but strictly greater than. So that's the proper subgraph, is just that one of these is a proper subset, either the edges or the vertices. Okay, so note that for the set V1 and E1, right, where these are the sets within the subgraph, to be a graph, the edges in E1 must originate and terminate at vertices in V1, right? So if we remove, what that's saying is that if we remove a vertex, right, from that original graph, then we have to remove any edges associated with that vertex. So let's say that we have a graph of the interstate highway system, right? And we remove, and we discuss some subset of that system. We can discuss it in terms of cities, right? But like if we're just discussing cities like along the south, right? Then we have to get rid of any, or then we cease to discuss any roads that lead past whatever, right, past Kansas City or whatever roads we're considering, leading further up north or further east or further west, right? So it's essentially, so if you restrict the vertices, right, then you have to clean it up and remove any edges that go to some vertex that isn't included in your graph, right? Okay, otherwise it's not a graph, it's a road to nowhere, right? And then restating, so if a node is removed from the original graph G, you must also throw out edges associated with that vertex. Okay, so now we can talk about isomorphisms. So two graphs are said to be isomorphic if there exists a one-to-one correspondence between their vertex sets, which preserves the edges. So an isomorphism you can think of as just a relabeling, right? Or some change in representation. So we can have these graphs of a network or of the highway system or whatever, but then if we start to store the data in some persistent manner, then this is the formal, like this is a definition, right? It's not exactly a theory. We're just saying that we can come up with these alternative representations that will be exactly the same. So if instead of referring to them by city name and highway name, we store them in a database, and now there's a city ID and a highway ID, right? Something that is a key to the database. Well, we're no longer referring to them by their interstate name or by their city name. We're referring to them by something else, but it's exactly the same thing, right? Because all of the connections are exactly the same as they were before. We're just relabeling it, essentially. We're storing it or representing it in some alternative manner. So that's the idea of an isomorphism, is that it's exactly the same. All you've done is really change the labels. Okay. So we'd say that they are isomorphic if for every pair of vertices V1 and V2 in our original vertex set V, and vertices U1 and U2 in our modified vertex set U, where F maps V1 to U1, right? So we've changed from city name to city ID, right? And that same function maps V2 to U2, right? So it's a second city ID. And any edge connecting V1 to V2 has an analog which also connects U1 to U2, right? So this is by definition. We haven't done anything other than say that we can do such a thing, like we can imagine such a thing, and when we do it, it's called an isomorphism. Okay, so Informally, an adjacency matrix is the matrix form of a graph, right? So here's a graph, here's the adjacency matrix. For example, given some set of vertices A, B, C, and D, for graph G, we have the let E represent the edges connecting the vertices. For the given graph G, consider this example, right, the hourglass example. Then the adjacency matrix, right? There's a 1 if the pair connects, right? So AA, right? There's no loop back on A, but A does connect to B, right? So A connects to B, and then symmetrically, B connects to A, right? So B connects to A. B connects to C, right? So BC. So C also connects to B, right? Because undirected graphs have that symmetry property. And so we fill out the graph like that, right? But we can omit the label if we want and just have the matrix. Okay. So next definition. Suppose that we have some graph, which again is a pair of vertices and edges, and it's simple such that the number of vertices is equal to n. So then suppose that the vertices in our graph are listed arbitrarily, right? We just have them listed in some arbitrary order. Then the adjacency matrix A, or our adjacency matrix of our graph, we can denote it either way, right? With respect to this listing of vertices, is the n by n 0, 1 matrix with 1 as its ijth entry when vi and vj are adjacent, so whenever there's an edge connecting these two vertices, and 0 if there is no edge connecting them. So in other words, if its adjacency matrix is A equals this set of entries for our matrix, then the value of those entries is 1 when there's an edge connecting I and J, right? So the row I, column J, right? And 0 otherwise, right? So we were just doing it. This is the definition for what we were just looking at. Now we define an incidence matrix, right? So adjacency matrices are vertex by vertex, right? Rows and columns are both vertices. Down here, we'll have rows or vertices and edges. The columns are edges for the incidence matrix. Right? So again, we have a graph, set of vertices and edges. We have the arbitrary ordering of vertices. Maybe not so arbitrary, right? If it's numbers, then they'll typically be sorted, in ascending order. If it's letters, then they'll be sorted in ascending order. But if it's by ID, then the order in which they were entered and received their serial number is somewhat arbitrary. So they're given some ordering, right? We're able to label them and trace it back, right? So then we have the vertices and then the edges, right? And the incidence matrix with respect to this ordering is the n by n, so it's not a square matrix anymore, at least not necessarily. It might be, but in general it probably won't be. So it's the matrix with these entries, and so here it's a 1 whenever the edge, so E1 connects V1 and V2. So each edge, each column is going to have exactly 2 1s, right? So every edge is going to connect to 2 vertices. Right? So there's always going to be 2 non-zero values per column, and that'll describe which vertices are incident with respect to that given edge. Right? Okay, so that's an incidence matrix. I tend to prefer adjacency matrices, but I will I will enforce that you understand both of these concepts. Right? So consider this graph, right? The vertices v1, v2, v3, v4, and then there's 4 edges, e1, e2, e3, and e4. Then it produces this incidence matrix, right? And again, the values for each edge are 1 whenever the vertex is connected, or the pair of, if the vertex is incident with that edge, right, or incident with another vertex along that edge, then it has a value 1 and it's 0 otherwise. Right? Okay. So now, the simple graphs G1 and G2 are isomorphic if there exists a 1-to-1 and onto function f, which maps from V1 to V2 with the property that A and B are adjacent in G, or in G1. If and only if f of A and f of B are adjacent to G2 for all A and B, V, such a function f is called an isomorphism. 2 simple graphs that are not isomorphic are called non-isomorphic. Okay, so here, earlier I'd said that an isomorphism, whenever, and again, this is a definition, this isn't a theorem, there's nothing here. This is just saying that f is your relabeling function, right? So if f appropriately relabels everything from your original graph to your new graph, right? So from the one that describes cities and interstates to the ones that describe records in a database table, then that mapping, your function, which does that mapping, is called an isomorphism, right? And then if you have 2 simple graphs that are non-isomorphic, then they're non-isomorphic. Okay, connectivity. So now we're going to talk about path connectedness. So before, whenever we said connected, we meant that there's an edge that directly connects vertex A to vertex B. And now, as we move forward, we're going to be more concerned with path connectedness. So maybe not an edge directly, but in terms of a network, can a packet be routed from your computer to some destination computer? And so in terms of computer science, that is the more interesting connection, or the more interesting interpretation of connectedness. Okay. So informally, a path is a sequence of edges that begins at a vertex of a graph and travels from vertex to vertex along edges of the graph. As the path travels along its edges, it visits the vertices along this path, that is, the endpoints of these edges. Okay. So I just want you to get used to the terminology a little. So vertices, you should already be familiar with. The path is just, it's the edges or the sequence of vertices. Right? And so, or sometimes we'll call them hops, whatever. But visiting essentially means that it is rerouted by that node, or it's forwarded by that node. And so that's the concept. That's a very subtle way to introduce that term, but it's an extremely common way to discuss it. So, okay, so a path is the sequence of vertices or edges, but the sequence of vertices that are visited in going from your point of origin to your point of destination. Okay, so the formal definition for a circuit, cycle, whatever, a path of length greater than 0 that begins and ends at the same vertex is called a circuit or cycle. A path or circuit is called simple if it does not contain the same edge more than once. So, so the paper route was the example that I gave before, but the optimal paper route, where you never travel along the same road or reverse direction along the road, is called a simple circuit, right, or a simple cycle. Okay. An undirected graph is called connected if there's a path between every pair of distinct vertices of the graph. So your network is connected or fully connected or whatever, or every device on your network is connected, essentially if everything can reach the router. So if it can reach the router, then they can all talk to each other on the same network, right? So it's exactly what you would think of in terms of a computer network. An undirected graph that is not connected is called disconnected, right? So if there's some computer that's offline, we would refer to it in that terms, it's offline because it's disconnected from the router, right? Okay, so we say that we disconnect a graph when we remove vertices or edges or both to produce a disconnected subgraph. So if everything is connected because of the router, and you take out the router, then you have a disconnected network. So this is a theorem. There's a simple path between every pair of distinct vertices of a connected undirected graph. Okay, so all that's saying is that if everything is on the same network, then you can go without repeating yourself or backtracking or whatever. You can go from A to B from any pair of computers on your network, without having to repeat yourself. And so it's kind of intuitive, but it's nice to know that there's a theorem that states that. Okay. Back to the definitions. So a connected component of a graph G is a connected subgraph of G that is not a proper subgraph of another connected subgraph of G. That is, a connected component of a graph G is a maximal connected subgraph of G. Okay, so let's say you have a huge office, right, or an office and a warehouse attached. And so the warehouse has its own subnetwork, and the office area has its own subnetwork, and they're both connected to some router which provides internet service. So because of that router, which deals with all outbound traffic and connects you to your ISP, the office and the warehouse are both connected. All the machines in both areas are connected. You have a true intranet. Right? But if something happens to the router, then those two areas, those two regions or whatever, become two distinct subgraphs, right? And so they are both connected components where they're, every device can see each other within that subnetwork, but the two areas can no longer see each other because you lost that one vertex. And so you go from one connected component, one intranet, to two connected components, right? These two distinct subnetworks which can't talk to each other. Right? Okay, so that's the idea of a connected component. Right? It's that maximal connected subgraph. Okay, so then now we're going to discuss cut vertices, and so this is exactly our, in terms of networks or sabotage in the case of a roadway or whatever. So are there any critical points in your network that if you remove either an edge or a vertex, that that you're able to disrupt communication within the network? Like, can you do it with just a single removal? And so this is in terms of what you want to consider whenever you're considering redundancy or failover. Where can it all go wrong really quickly? So vertices whose removal from a graph and all incident edges. So if you remove the computer or the router or the switch or whatever, you don't necessarily have to remove the cabling, but whenever you're representing it, if the vertex is gone, then the edge needs a terminal point, right? So whenever you're representing it logically, you remove the edges as well as the vertex. So you remove it from the graph, and it produces a subgraph with more connected components. Well, such a vertex, such a critical point or ideal sabotage point is called a cut vertex, or the collection of them is called the cut vertices, right, or articulation points. The removal of a cut vertex from a connected graph produces a subgraph that is not connected. And keep in mind that we've said that multiple connected components, right, would result. And so not connected and multiple connected components, perhaps counterintuitively, are essentially the same thing. So it just means that you've broken it, right? It's no longer integral. It's no longer a single thing. Now it's broken, and how many pieces did it break into, right? And so the number of pieces that it broke into are your connected components, and because it broke, we would say that it's not connected. Okay, so analogously, an edge whose removal produces a graph with more connected components than the original graph is called a cut edge or a bridge. So note that in a graph representing a computer network, a cut vertex and a cut edge represent an essential router and an essential link that cannot fail for all computers to be able to communicate. So in the example where we had the router that was connecting the two areas, the office and the warehouse, then that would be a cut vertex. Or if you had one of the cables get chewed through by mice or whatever, then that would be a bridge or a cut edge that could completely disrupt communication. Okay, so definition. Connected graphs without cut vertices are called non-separable graphs. And so these are going to be, in terms of computer networks, they're going to be networks with failover described, where routing has multiple paths that can succeed in case of failure. Okay, so we will do. Let's see if we can make it through this theorem, and then we'll start 10.5 next time. Okay, so next definition, define kappa of G as the function which counts the connectedness of the graph. That is, kappa of G declares the minimum number of vertices that must be removed from G in order to separate the graph into multiple connected components. So this is your measure of redundancy. So if this is 1, then it means there's a single ideal sabotage point. If it's 2, then you have to have 2 components go down before it breaks down. If it's 10, then you have to have 10 components go down before you experience the disconnected state. So in terms of networking, this is how many routers, laptops, phones, etc. would need to be removed before at least one device on the network could no longer ping Google. We say that a graph, so if you're tethering, right, through a cell phone or whatever, then if your phone battery dies, then you lose internet, right? So kappa of G of a network in a car that's driving along and using your cell phone as a hotspot has a kappa of G value of 1, right? Your connectedness is of degree 1. Okay, so we say that a graph is k connected or k vertex connected if kappa of G is greater than or equal to k. Okay, so then a directed graph is strongly connected if there's a path from A to B and from B to A whenever A and B are vertices in the graph. So in an undirected graph, this is always true. If you can get from A to B, then you can get from B to A by just reversing direction. But with one-way streets, right, or where you're going only in one direction, then you're not guaranteed to be strongly connected. And so you have to, in order to satisfy the definition of strongly connected, if you want that, then the property that you have to test for is that anytime you get from A to B, that there's a way to get back from B back to A. So in smaller graphs, like if you're just given it, then you can analyze it and ensure that anytime for every path connected pair of vertices A and B, that it is also path connected from B to A, or you can disprove it potentially to show that it doesn't have this property. But if it's a larger network and you're analyzing it algorithmically, then you would want some analytical way to do it, or you would want your computer to count all of the connections to make sure that this property is satisfied if you want to claim this property. But we just offer it as a definition here for a way to describe that symmetry of path connectedness. Okay, so in terms of networking, this would imply that any two devices on the network could share files between them, right, or SSH sessions or any other form of network chatter. Right? But it means that it can be initiated from either machine as well. Right? This is not the case when one of the devices on the network is hidden behind a firewall, such as a home computer protected by the firewall of a router. Right? Okay, so next. A directed graph is weakly connected if there is a path between every two vertices in the underlying undirected graph. Okay, so again, I said that this condition is this symmetry condition of path connectedness is always satisfied in undirected graphs. So this says that if every pair is path connected, then it's weakly connected. Right, if it's path connected with respect to the undirected one. But if you account for a directed graph, right, then there is that stronger condition where if it's satisfied, we can say that it's strongly connected. Right? So an example of a graph which is weakly connected but not strongly connected is a community of radio listeners. Right? So the radio signal is broadcast out unidirectionally from a single source and everyone is connected, and that they are listening to the same broadcast, but communication between all members of the network or graph has not been established. Okay, so we end with the theorem. Let G be a graph with an adjacency matrix A, given some ordering of the vertices, right, with directed or undirected edges. We don't really care right now, with multiple edges and loops allowed. Right. So then we say the number of different paths of length r from vi to vj, where r is a positive integer, equals the ijth entry of a to the r. So before we use this to represent the transitive closure property, right? And now we see that it carries over. And so if we count the vertices, right? So if instead of using a 0-1 matrix, we use a matrix where it's 0 if two edges are not directly connected, and 1 each time they're connected. Right? And so if they're doubly connected, then it has a 2 and it's in that adjacency matrix entry. Right? Then we can use matrix multiplication, right, to sort of count up the different paths. Right? So that transitive property carries over. And so the number of different paths of length r can be derived from that, from matrix multiplication or exponentiation if you prefer, and then counting those values, taking advantage of the degrees of those vertices. Okay, so another unexpected but really cool property of matrices, right? If solving systems of linear equations wasn't interesting enough. Okay, so that'll do it. I haven't decided whether or not I'm going to give you a homework this week. I'm leaning towards no, but if I haven't assigned it by by the time you watch this recording, then I am not going to assign one this week. All right, have a great weekend, and I will talk to you all on Tuesday.